Hello, this video is for Chapter 3, Lesson 4. It's titled Solving Inequalities Using Addition or Subtraction, where we'll solve inequalities using addition or subtraction. Our vocabulary for this lesson is inequality, solution of an inequality, and equivalent inequalities. So, inequalities, what are they? Well, we've been working with equalities, where two things are equal. And now we're going to talk about inequalities, and inequalities are whenever we're dealing with something to where something is greater than something else or less than or something else, could still be equal to, and we'll talk about that as well. And we're going to find that there are a lot of similarities between equalities and inequalities, and what are those similarities, and then also what are some of the differences. So let's go ahead and get started. An inequality is a statement. It's formed by placing an inequality symbol between two expressions. For example, y plus 5 is less than or equal to -6. This is an inequality. So this sign right here that looks like the arrow pointing left with a line under it, that sign, we read that as is less than or equal to. We see all of those signs down here in our example of inequalities. Right here, the first one where the arrow's pointing left, we read this as is less than. Here, arrow point to the right, we read this as is greater than. And then this one here with the arrow to the left and the line under it, we read this as is less than or equal to. And then with the arrow point to the right with the line under it, we read this as is greater than or equal to. The solution of an inequality with a variable is a set of all numbers that produce a true statement when substituted for that variable. You can show the solution of an inequality by graphing the inequality on a number line. So just as you graph points on a number line for values whenever we're looking at finding out where a number would go on a number line, we're going to do the same with inequalities as well. When you graph an inequality in the form of x is less than a, or x is greater than a, or x is less than a, got those two confused, you use an open circle at the point A. Such as here, we see this open circle here. We have x is less than 3, so we have an open circle here, and y is greater than 2. At 2, we have an open dot there, and we'll talk about what that open dot means. When you graph an inequality in the form of x is greater than or equal to a, or x is less than or equal to a, you use a closed circle at a. So here where we have z is less than or equal to 4, notice that at the point 4, we have a closed dot. And n is greater than or equal to 2, we have a closed dot here at the point 2. So let's look at some of these examples that we have here at the bottom of this page. Here in our inequality of x is less than 3, this is all numbers that are less than 3. And so on a number line, we know that all the numbers to the left of another number are less than that number. So that's why this arrow is pointing to the left. It's showing all the numbers that are less than 3. Notice that 3 is not included. That's what that open dot compared to that closed dot means. This means that that point is not included. So in this case, 2.99999 would be a solution, but 3 is not a solution. That's why we use an open dot to show that we are not including that point. Here we have y is greater than 2, all numbers greater than 2. Well, we know that on a number line, all the numbers to the right of another number are greater than that number, so therefore the arrow is going to the right. And again, 2 is not a solution, so it's an open dot. Now, however, these next two examples here are a little bit different than our previous two examples. Here we have half of an equal sign along with it, right? The bottom half of an equal sign. So here we have z is less than or equal to 4. We read that as all numbers less than or equal to 4. So again, to the left, everything is less than. And it could be equal to 4, so we're going to include 4. That's why we have a closed dot. And then on the last one, n is greater than or equal to 2, so it could be equal to 2, so it's a closed dot. and also everything that's greater than, so we have everything to the right of 2. All those numbers are greater than 2 because they're to the right of 2 on the number line. So kind of get an idea of it, the main thing here that we noticed is that the difference between whether or not we have the equal portion, such as in the bottom two here, or whether we don't have the equal portion. If it is not equal to that number, it has to be either greater than or less than. Use an open dot. If it could possibly be equal to that number, meaning that we have the inclusion of the bottom half of the equal sign, then we're going to use a closed dot to show that those 2 points, or that point is also a possible solution of the inequality. Looking at the next page here, example 1, writing and graphing an inequality. It's science. The freezing point of water is 0 degrees Celsius. At temperatures at or below the freezing point, water is a solid, also known as ice. Write an inequality that gives the temperature at which water is a solid. Then graph the inequality. So our solution is we're going to let T represent the temperature of the water. That's a good variable to choose because temperature starts with T. Water is a solid at temperatures less than or equal to 0. So it could be right at 0 or anything less than 0. So since 0 is a solution to this, we're going to use the equal concept as well. And we're going to make sure we have a closed dot. And then all the numbers less than 0 are to the left, so our arrow goes to the left. Here we have some penguins on a glacier. That's nice. So solving inequalities. We're going to find that solving inequalities are a lot like solving equalities. You can use the following properties to find the solutions of inequalities involving addition and subtraction. Using these properties, you can write equivalent inequalities. Equivalent inequalities are inequalities that have the same solution. So whenever we talked about equalities earlier in our course, we talked about, we could think of it as a scale, right, where everything's balanced. And if we have everything balanced, whatever we have on the left side would also be equal to whatever we have on the right side. And I'm getting caught up in making sure I draw my cubes there. So we have two things that are balanced. However, with inequalities, we're talking about where something's not balanced. So let's go ahead and we'll leave our little fulcrum there. That's where two things teeter on. And I'm going to try to draw a line that goes down through that. Kind of steep there. Maybe I could go ahead and extend my base of that a little bit so it looks correct. There we go. So in this case, we're talking about where we have something over here that weighs less than whatever's on the right. So I'll just use a different color since I don't want them to be the same thing. So we're going to say that the red block is heavier than the blue block. So here we have an inequality where two things are not equal. Well, let's see what this has to say about the addition and subtraction property of inequality. In words, we say that adding or subtracting the same amount on each side of an inequality produces an equivalent inequality. So if A is less than B, and we add C to both sides, then A minus C is going to be less than B minus C. And as I said that, I realized that I read that incorrectly. We're saying that if A is less than B and A plus C is less than B plus C, then if we take C from both sides, then A is still going to be less than B. And likewise, if A is greater than B, then A plus C is greater than B plus C. Then if we take C away, then we end up with A still being greater than B. So the inequality sign is not going to change. And I think I really kind of messed that up in trying to explain that, but let's look at it picture-wise. So let's say that we have another block. Let's say we have a green block, and we don't know what it weighs, but we do know that green ones weigh the same as the red one, or green ones weigh the same as each other. Well, if I add a green one on each side, I'm still going to end up with the same deal of where the left side over here is lighter than the right side over here. So we're talking about weight. Let's call this we'll call this the A side, and we'll call this the B side. Then A is still going to be less than B. And likewise, if we started off with this, that blue plus green is less than blue plus red, or green plus red. Don't know my colors today. If I go ahead and subtract green from each side, the A side is still going to be less than the B side. So basically, whatever you do to one side, if you do it to the other, then the inequality remains the same. And that's kind of like what we had with equations when we're talking about properties of equality. If two things were balanced, whatever you did to one side, you did to the other, the balance remained. In this case, if you have an inequality, whatever you do to one side, if you do it to the other, then you're still going to have that same inequality going on. So here in example 2, solving an inequality using subtraction. So we have solve m plus 5 is less than or equal to 10. And then it wants you to graph and check your solution. So we're going to rewrite the original inequality. M plus 5 is less than or equal to, or is greater than or equal to 10. So the 5 is tied to the m through addition. So we're going to subtract the very number we wish to get rid of, which is the 5. So we're going to add negative 5, and what we do to one side, we do to the other. The positive 5, negative 5 are going to cancel each other, leaving us with just m. 10 minus 5 is 5. And so we end up with m is greater than or equal to 5. So the solution is m is greater than or equal to 5. So to graph this, we find the point 5, graph it. It does include this concept of equality as well. It could be greater than or equal to, so we want a closed dot. And it's all the numbers greater than 5, so we want the arrow to the left. Now notice that the arrow on our graph goes, I said to the left, it's to the right. So notice that our arrow goes to the right, and also the inequality symbol has an arrow that's pointing to the right. So our m is on the left, our variable is on the left, the number that we're plotting is on the right, and the arrow points to the right, and the arrow on the graph goes to the right as well. So now choose any number that's greater than or equal to 5, substitute the number into the original inequality, and then check and see if it's true. So we have m plus 5 is greater than or equal to 10. Let's pick 8. 8's greater than 5, right? So 8 plus 5 is 13. Is 13 greater than or equal to 10? Indeed, 13 is greater than 10, so our solution checks out. Solving inequalities using addition. So on our last one, we used subtraction to solve the inequality. Now we're going to use addition. So solve negative 10 is greater than x minus 12. So rewrite your original inequality. Negative 10 is greater than x minus 12. The 12 is tied to the x through subtraction, so we're going to use the opposite operation, which is addition. We're going to add the very number we wish to get rid of, which is this 12, so we're adding 12. And what we do to one side, we're going to do to the other. Now we have negative 10 plus 12 equals positive 2. The negative 12, positive 12 cancel each other, leaving us with just the x. And we end up with 2 is greater than x. So the solution is 2 is greater than x, or x is less than 2. Well, notice what they did right here. We have 2 is greater than x, which apparently is the same thing as x is less than, or equal, well, actually x is just less than 2. So we graph it. We're going to have an open dot right here because it does not involve the equality portion. And everything less than 2 is to the left. And notice that our arrow on the line, or on the graph, is going to the left, and also the inequality symbol points to the left as well. But notice over here where we had 2 is greater than x, the arrow pointed to the right whenever the arrow on the graph went to the left. However, it seems to be that if we flip it around and we always keep our variable on the left, that whatever the arrow is on the inequality statement, with our inequality statement there, whatever that arrow, whichever direction that arrow is facing, is also the same direction that we put on our graph. And here on the left we see reading algebra. We note that you can read an inequality from left to right as well as from right to left. For instance, the solution of example 3 read 2 is greater than x. Well, it can also be read as x is less than 2. So here's our checkpoint here. Let's do a couple on the checkpoint. We'll do 1 and we'll do 3. So we have n plus 7 is greater than 3. The n is tied to the 7 through addition. We're going to use subtraction. Going to subtract the very number we want to get rid of, and whatever we do to one side, we're going to do to the other. The sign's going to stay the same. 7s will cancel each other, leaving us with n. And 3 minus 7. This is like what, 3 plus a negative 7, actually. So the difference between them is 4. 7 minus 3 is 4. And the negative 7 has a greater absolute value, and it's negative, so we're going to make our answer negative as well. So we end up with negative 4. And if we were to graph this, here's 0, and here is negative 4. It does not have the equality portion, so we want an open dot, and then we're going to highlight everything to the right, because everything to the right is greater than negative 4. And again, notice that my inequality sign looks like an arrow going to the right, and on my graph, my arrow went to the right as well. On the next one over here, number 3, we have negative 6 is less than or equal to x minus 9. So let's get the x by itself. Well, the 9 is tied to the x through subtraction. Opposite operations addition. 9 is the number we want to get rid of. And whatever we do to one side, we do to the other. Our sign's going to stay the same. The 9 is going to cancel each other, leaving us with just x on the right. Then negative 6 plus 9. So this is negative 6 plus 9. Well, we learned earlier that we could actually find the difference between the two. So 9 minus 6 is 3. And the 9 has the greater absolute value, and it's positive. So our answer is going to be positive. So we end up with 3. Now, so that this sign here, this inequality symbol, helps me on the graphing, I'm going to flip this around. The x is going to go over on the other side. The 3 is going to go over on the right side. And now I need to flip the sign. And now I can go ahead and graph it. Here's 0. Here's 3. And notice the equal portion of it. So I need a solid dot. If you're thinking solid dot, then good answer. And then shade everything to the right. So everything greater than or equal to 3. Here we are, example number 4, writing and solving inequality. Triathlon. You are competing in a triathlon, a sport competition with 3 events. The key prefix there is tri, right? Tri means 3, like a tricycle, has 3 wheels. So triathlon, sports competition with 3 events. So last year you finished the triathlon in 85 minutes. The table shows your times for this year's first 2 events. What possible times can you post in the running event and still beat last year's finishing time? So here we have a table. It's titled Triathlon Times, because all tables should have a title. Then you have 2 columns, one for the event, the other for the time. And good thing they've labeled time in minutes so that we know that it is indeed minutes. We have the events, swimming, biking, and running, and their corresponding times. Swimming 17, biking 45. The question is, what about running? And we want to find a time that's going to beat last year's time. So we're going to let T represent this year's running time. So T is what we don't know, that question mark. We're going to consider that a T now. That's going to be our variable. Write a verbal model. So first we have our swimming time plus our biking time plus whatever our running time is, which is what we don't know. We're calling that, well, we're not calling it X, we're calling it T, aren't we? And we want that time should be, in order for it to be better than last year's time, it has to be less than last year's finishing time. So let's plug everything in. Swimming time, 17, we get it from the table, plus the biking time, 45, again, we get that from the table, plus whatever our running time is, we're calling that T, and we want that to be less than whatever last year's time was, which we got from the sentence up here at the beginning, or the description, or the paragraph at the beginning, 85 minutes. Now we substitute everything in, now we can go ahead and solve. So let's go ahead and simplify by first adding the 17 and the 45 together to get 62. Bring down that plus T, less than 85. Now we need to subtract 62 from each side. So we're going to add a negative 62, which we see here. What we do to one side, we do to the other. So we have that here. 62, negative 62 are going to cancel each other, leaving us with T. And 85 minus 62 is 23. bringing down our less than sign, so t is less than 23 minutes, or 23, and remember that's going to be in minutes, right? So our answer is, to beat last year's finishing time, you must post a time in the running event that is less than 23. So notice that we use the less than sign because 23 wouldn't cut it. 23 would have been a tie with last year's time. We want to be better than last year's time, so we would not include the equal concept in there. We'd say we want it to be less than. Now, we don't have an exact answer because we could do it in 23 or less. So 22, 21. Now, -7 is less than 23, but that wouldn't make sense in this problem because there's no way you could have a -7 minutes for running, right? So we understand that it is going to be anywhere from, well, it would have to be greater than 0, and but less than 23. And obviously, it's probably just going to be a little bit less than 23. Chances are we're not going to, whatever we ran last year in 23 minutes, we're not going to run in 2 minutes this year. So over here on the left, we have a picture of the Ironman triathlon in Roth, Germany. So a bunch of people out there in the water swimming. All right, for a guided practice, what are equivalent inequalities? Well, if we look back here on this page here, we see that equivalent inequalities are inequalities that have the same solution. So if you have two inequalities and their solutions happen to be exactly the same, then they are indeed equivalent inequalities. Next is explain how the graph of x is greater than 5 is different from the graph of x is greater than or equal to 5. Well, hopefully you're spotting this part right here is different. The signs are a little bit different here, right? Over here we have x is less, or x is greater than 5. And over here we have x is greater than or equal to 5. That means if we were to graph them, because they're saying how is the graph different, if we were to graph them, the first one we would have 5 and an open dot because 5 is not included, and then everything to the right. But if we were to graph this other one, wherever 5 is on the number line, it would have to be a solid dot because 5 is included. We know that because it has the equal portion in the inequality symbol. And then it's everything to the right. So they're very similar. It's just that the first one would be an open dot. The second one would be a closed dot. On the next section, tell whether the given number is a solution of -5 is less than n. So if we just plug it in and substitute it, then we could see. So on the first one says 8. So wherever n is, we're just going to substitute 8. Is -5 less than 8? Indeed it is. That one checks out. If we plugged in the next one and we said -8 here, -5 is less than -8. Well, not actually if you think about it. -8's here on the number line. -5 is to its right, so -5 is actually greater than -8. So this one doesn't work out. On the next one, what about -4? Well, where's -4 on the number line? Well, that's like right here, right? So is -5 less than -4? Indeed it is. And then the next one looks pretty easy, right? Next one's 4, right? If we plug in a 4 there, well, on the number line, 0's here and 4's down that way someplace. So -5 is definitely less than +4. So 3 of them checked out, 1 of them didn't. All right, next we are asked to solve the inequality, graph and check your solution. So let's go ahead and do 8 and we'll do 10. So fit it in over here to the side. So let's rewrite it. 1 is greater than or equal to x minus 9. So the x is tied to the 9 through subtraction. The opposite operation is addition. It's 9 that we want to get rid of, and what we do to one side, we do to the other. So the 9's are going to cancel each other. Our sign's going to stay the same. 9's cancel each other, leaving us with the x, and 1 plus 9 is 10. I think they ask us to graph it. Indeed they do. So if we made a graph, and we had 10 here, and notice that my variable is on the right. I could flip it around. I could put the x on the left, the 10 on the right, but I also have to change the sign the other way. And now I can go ahead and graph that 10, and it's going to be a closed dot because notice that I have the equality concept in with this inequality sign. So it's less than or equal to, so it's closed dot because 10's included. And then graph everything to the left of 10, just like the arrow shows here. And indeed, those are all values that are less than 10. On the next one, go ahead and erase this here. We have x plus 3, and that is greater than 7. So let's go ahead and notice this is a lot like solving equations, right? It's just a different sign, right? So x plus 3, the 3 is tied to the x through addition. The opposite operation is subtraction. We're going to subtract the very number we wish to get rid of, which is 3, and what we do to one side, we do to the other. The positive 3 and negative 3 will cancel each other, leaving us with x. Let's bring down that sign there, greater than, and 7 minus 3 is 4. Good, the variable is on the left, so I can just leave it over there on the left because that's going to help me graph. I'm going to find 4 on my number line. I'm going to do an open dot because notice this just says greater than. It doesn't have the equality concept, so it's open dot, and the inequality looks like an arrow pointing to the right, so I'm going to shade everything to the right. And let's see, does this seem to be true? X is greater than 4. If I picked another number like maybe 6 down here, is 6 greater than 4? Indeed, that is true, so I seem to have drawn my arrow in the correct direction. So that's everything I have for Chapter 3, Lesson 4, Solving Inequalities Using Addition or Subtraction. Thank you.